Today's talk. And so thank you so much for joining our session on rigor and reproducibility back to basics. My name is Lindsey. I'm your moderator for today's 45-minute session. And presenting today, we have Dr. Patricia Valdez. Dr. Patricia Valdez is our extramural research integrity officer. And our format today will include a presentation, followed by some time for Q&A with Dr. Valdez. We do have our colleagues on the back end who will be answering some of your questions as they're coming in the chat during the presentation as well. So thank you for joining us here. Patricia, you take it away.
Okay, great. Thanks so much, and welcome to rigor and reproducibility back to basics. Hopefully I can move the slides here. Okay. Did move on your side.
It didn't actually. Oh, there you go.
Okay, got it. Okay, so I'm going to be talking about a couple different things today. So first, we're going to talk about, why are we concerned about reproducibility? Then I'm going to talk about the NIH response, including, including application updates that we made. And again, that'll be addressing rigor and grant applications, and then we'll talk about training and resources at the very end. Okay, so the reproducibility challenge. Now, this is something that we've been hearing across the media, as well as by amongst our researchers. The initial interest in this, or I guess concern with reproducibility, came about about 2011 to 2013. There were a couple of drug companies that were trying to reproduce data in order, of course, then to go on to develop drugs. And what they found is that for a large number of the studies that they attempted to reproduce, they were unable to. And so we had a lot of publications came out about the issues, drug targets sliding away, and something like that. This is really, it became very pervasive at that point. Looking on it is that a lot of the concerns were around clinical research. One thing that I really mentioned about those studies that the pharmaceutical companies that were attempting to reproduce the studies in journals was that we didn't really know exactly what studies they were not able to reproduce or replicate. We don't have a really good sense of how many exactly we're talking about. So those studies were not very transparent in themselves. So. Now, the NIH was actually concerned about this issue even before this all came out in media in 2011, 2013. So that's around 2002. There were several studies that were conducted about a drug called minocycline. This drug was shown to, in preclinical animal models, shown to increase survival of SOD1 mice. This is a model for ALS. So based on the preclinical data, NINDS funded a clinical trial and enrolled hundreds of patients. They were given the drug minocycline and followed, and basically they had no improvement, nothing happened. And so at that point, NINDS decided to go back and try and figure out, what happened, why did this trial fail so miserably? And so when they went back and looked at those 2002 papers, they found that a lot of those papers actually were not very transparent in reporting. They didn't indicate whether or not the animals had been randomized, if there was blinding. In some cases, they didn't report the sex of the animal, or they didn't report the transgene number, copy number of those mice. So there were some issues there. And so in response in 2012, they got a group together and they published this article, which is basically a call for transparent reporting to optimize the potential value of preclinical research, and really outline the need to be transparent when you report preclinical work, including, as I mentioned, including information on whether things like the animals were randomized, whether there was blinding, how the data were handled. Now, there are challenges to rigor and transparency in reporting science. Now, we often think of science as being self-correcting. So eventually we'll get to the right and the correct piece of data or the correct information. And so does that mean that science is immune from reproducibility problems? Probably not. But the principle does remain true over the long term. So we will eventually get to the true answer or closer to the true answer. But in the short and medium term, there is interrelated factors that will source of that correction, even if it extends that time frame. And this is the reproducibility problem. And there's a lot of time, money, careers, and public confidence. And there's a lot of collateral damage when things cannot be reproduced. So what are some of the factors that might short circuit self-correction? So one is for training. So it's possible that individuals may not have been properly trained in experimental design. There could be inappropriate use of statistics. So if individual didn't learn how to properly use statistics. There's something called p-hacking, where you have the data and then you basically take the data, find, like I said, what I say, torture it enough so you get your p-value to be at the right value you want it to be. So really, manipulating the data at that point. There could also be incomplete reporting of resources used or unexpected variability in resources. And so this means, for instance, if there's a cell line that is being used in a study, is later found to actually be misidentified cell line. And so we'll talk more about this in a second. So it's possible that you may be using a reagent or a cell line, but you think it is one thing, but it's actually another. Other factors that can short-circuit self-correction are publication practices. So we all know there's a difficulty in publishing negative findings. And there's also an overemphasis on the exciting big picture findings that leaves out necessary details. And so we've seen this for many years. We saw that the method sections of papers were shrinking and shrinking, and hopefully we're starting to reverse that trend. There's also the current hyper-competitive environment. Now, we know there's historically low funding rates, and also grant review and promotion decisions really depend too much on those high-profile publications. And so someone who is trying to get a grant or trying to get a promotion may tend to take shortcuts. Now, so in 2014, NIH published a couple of papers, and these are perspectives and plans on how we might want to address reproducibility. Now, so this first one came out again in 2014, and it laid out our plans to update grant applications with language that would further allow us to be able to determine whether or not the proposed research could be very robust and reproducible. And the one thing I want to note is this quote here says, efforts by the NIH alone will not be sufficient to effect real change in this unhealthy environment. And this is really important because again, we really need everybody working together to solve this issue. Researchers, institutions alike, as well as funders. That same year, another paper came out. So this was from NIH paper as a perspective, really telling the community that we were planning to make updates to grant applications to balance sex in animal studies and really in all the studies. So, this is over the course of fiscal year 2015, we rolled out policies that require applications to address the inclusion of both sexes in biomedical research. And because we know that, males and females can react differently to drugs, they may have disease that look different, for instance, heart disease. And so it's really important that, we're paying attention to those differences and that we are not always using one particular sex in certain studies. And then the third paper that came out of this perspective that came out in 2014 was by NIH with this one here you see. So it made a couple of points, all dealing with the problem with misidentified cell lines. So some of the points are here. So since the 1960s, more than 400 widely used cell lines worldwide have been shown to have been misidentified. And a 2011 study of 122 different head and neck cancer cell lines revealed that 37 or 30% were actually misidentified. So this is a big problem. And so we want to make sure that researchers are regularly checking their cell lines to make sure that they are working with the cell lines that they believe they are. And so this informed part of the policy that I'm going to describe now. So our guiding principles for rigor and transparency when we rolled out this policy were first, we wanted to clarify our long-standing expectation regarding rigor and transparency in applications. And so, we don't think that we're funding applications that were not rigorous in the past, but we wanted to clarify this need and make sure that, we do get applications that properly describe the research. We also wanted to raise awareness and begin culture shifts in the scientific community. We also wanted to improve the way that applicants describe their work to provide sufficient information for reviewers. The reviewers need to know more details in order to determine whether or not it looks like a proposal that could be successful. And as always, we want to make sure that NIH is investing in the best science and minimizing unnecessary burden. Okay. All right, so there were 4 areas of clarification. So the first area is called rigor of the prior research. Previously, it was called scientific premise, but many researchers, I think there was misunderstanding of the word premise, and so we call it now rigor of the prior research. Now, the second one is scientific rigor of the proposed research. And then the third one is relevant biological variables, such as sex, so we want to consider those. And then the fourth area is the authentication of key biological and/or chemical resources. Okay, and this all came out with in 2016 for applications that came in 2016. Now, this is an important chart. This is really showing you where in the application are each of these elements addressed. So we have on the left side, you see the element of rigor, and you see rigor of the prior research. Now, rigor of the prior research, if you look at the section, so it's in the research strategy. It's scored under significance, and it does contribute to the overall impact score. Now, rigor of the prior research is the only element that is actually scored in two different places. So we have it under the research strategy where it's scored under approach as well. And so this is, I'll talk more about this in a second, but this is really, if you identify any problems in the rigor of the prior research, you then tell us how you're going to address them. And this contributes to overall score. And then we have scientific rigor, and that's under research strategy. It's scored under approach, and it contributes to the overall impact score. Then we have consideration of relevant biological variables, such as depth, which is under research strategy, scored under approach, and contributes to the overall impact. And then finally, we have authentication of key biological and or chemical resources. This is actually an attachment. It's an additional review consideration. It does not contribute to the overall score, but reviewers will mark it as unacceptable or acceptable. Now, one thing with authentication, the authentication plan is that, if it's marked as unacceptable, that doesn't mean that the application won't be funded. The program official will then work with the PI and the institution to come up with an acceptable plan. Okay, so now I'm going to go through each of those elements in a little bit more detail and address some of the questions that we've had about them. As I mentioned, rigor of prior research is addressed under significance and then under approach. So under significance, we ask that the PI addresses the strengths and weaknesses in the rigor of the prior research that serves as a key support for the proposed research project. Now, when you're looking at the prior research, again, prior research can include some observations, the preliminary data, or published literature. We're going to assess the strengths and weaknesses of that data. And then under approach, we ask you to describe plans to address any weaknesses in the rigor of the prior research that serve as a key support for the proposed project. So again, so in the significance, you tell us about the strengths and weaknesses of the prior research, and then under approach, you tell us how you're going to address any weaknesses. Okay, so one question that we often get is, excuse me, what do I include when describing the rigor of the prior research? Now, so when you're assessing the rigor of the prior research, you could consider, whether or not there was an appropriate sample size in the prior research, whether the prior research, whether they stated there was randomization or blinding, did they use adequate positive or negative controls, they use appropriate statistical tests, did they consider relevant biological variable? So maybe they did all of the studies in male mice, and maybe they should have also looked into female mice as well. Authentication of key resources, for instance, if previous studies used a misidentified cell line, that could be considered a weakness, and then you might want to address that in the approach. Okay, so then the second element is scientific rigor. So we define scientific rigor as a strict application of a scientific method to ensure robust and unbiased experimental design, methodology, analysis, interpretation, and reporting of results. So in this section, this is under approach, we expect that you will describe the experimental design and methods proposed and how they will achieve robust and unbiased results. So one question we get around scientific rigor is how much detail should I include to address this? So we tell applicants to succinctly state what's planned. So you want to include information on sample size, estimation, effect size, whether you're going to blind study, how you're going to blind study, randomization, statistical analysis. And this is also where you're going to describe your experimental animal numbers and include your power calculation. Sometimes people will include that in the regular animal section, but we do ask you that you include that under approach. And you should be transparent about your plans for analysis, and of course, stay within page limits. Okay, so the third element is consideration of relevant biological variables such as sex. So we understand that different biological variables can affect health or disease, and those include sex, age, weight, and any underlying health conditions. So in the application, we ask that you explain how relevant biological variables such as sex are factored into research designs and analysis for studies in vertebrate animals and humans. So this applies to, again, both vertebrate animals and humans. Now, you can propose to study one sex, but you will need to provide a strong justification from the scientific literature or some preliminary data or other relevant considerations if you're going to do that. Okay, so the FAQ, or the frequently asked questions around this is, will I have to double my animal numbers? So, it's seriously doing all my studies in male mice, and now going to have male and female. So you may have to power your initial study to detect sex differences. Because we don't want to make everyone start to become, sex difference researcher, but we ask you to begin to collect data on sex for early stage research. So again, we think of research as a continuum where we have the early stages and then go into later stages. We really want to start understanding that information, the differences between males and females early on, and by the time you reach the late stage, you may have more information about, whether or not what you're studying is more relevant for males or females, and then you make the decision to study only one or the other. So again, the justification should be provided in the application if you're proposing to study one sex. Now, some of these justifications can be like if you're studying a sex-specific condition or phenomenon, for instance, ovarian or prostate cancer. If you're using an acutely scarce resource, for instance, if you have a complicated genetic class to get, these mice, and maybe the genotype of the mice is very rare, their interest is very rare, that could limit you as far as, using both males and females as equal numbers. And also, you can make a sex-specific hypothesis if you already know that there's differences between the males and the females. So again, that's another justification that you can provide. Cost and absence of known sex differences are inadequate justifications for not addressing sex. Okay, so the last element of the enhancing reproducibility through transparency is authentication of key biological and or chemical resources. So we know that the quality of established resources is critical. And again, this policy applies to established resources, not resources that you are developing or you propose to develop. Okay, these include cell lines that are already in existence, antibodies, chemicals, or mice, etc. And so for this part, we ask in the application that you provide a plan to regularly authenticate and ensure the identity and validity of your resources. So, and each investigator will determine which resources are considered key. Okay, so we did publish a subsequent reminder because we wanted to make sure that people understood, what to do or we'll be going here. So again, we further defined repeated our definition of key biological and or chemical resources and provided examples like cell lines, chemicals, genetically modified animals or cells. And specifically in the authentication plan, we said do not include any plans for authentication of data sets, databases, machinery, or electronics. And these is only for biological and or chemical resources. Do not include plans for the development and authentication of new key biological and or chemical resources. Again, that should be described in the application itself under approach. The authentication plan is only for established resources. Do not include plans for authentication of standard laboratory reagents that are not expected to vary. And don't include the authentication data and any other data in the authentication plan because you will risk the application being returned because you added information in document places where it shouldn't be. So make sure that you're not adding authentication data there in the authentication plan. Okay, and then I just want to quickly remind you that when you're submitting your progress reports, we are still looking at those progress reports with an eye for research rigor. So when we ask, what was accomplished in these goals, you'll have to provide more information how steps you've taken to ensure robust and unbiased results. And then when we're asking what you're going to plan to do, what are your plans for the next reporting period, you're going to include efforts to ensure that the approach is scientific and rigorous and results are robust and unbiased. So make sure that you don't ignore the rigor when it comes to the RPPR, the progress report. And I want to mention that one of the newest developments is that we've implemented training in rigor last year. So that means now this applies to institutional research training, institutional career development grant applications. And so we asked those applicants to describe how the program and faculty will provide training in rigorous research design and relevant data science and quantitative approaches. These applications need to also include a plan for instruction and methods for enhancing reproducibility. Okay, and all these things will contribute to the overall impact score. And in addition, for fellowships and individual career development, starting last year, they now are required to address as applicable any new research skills that they expect to acquire in the areas of rigorous research design, experimental methods, quantitative approaches, data analysis, and interpretation. So again, that also contributes to the overall score. Okay, and then I just want to point you to some resources here. So this is the NIGMS Clearinghouse for Training Modules to Enhance Data Reproducibility. NIGMS, along with other ICs, came together to fund modules that were created by the external community. And really the idea was that these modules would be useful and used by institutions as they're developing their training plans and where they need to incorporate rigor into their training plans. Okay, and this is our extramural websites on enhancing reproducibility through rigor and transparency. You'll find a lot of resources here. So if I were to scroll down, you would see the guidance. You would see the resources here, which include the scientific rigor examples, resources and tools for rigorous experimental design, authentication plan examples, and more. And the training is here as well, and then notices. There's some of the items you can find here, including this infographic. I won't go through this in detail. Also, this chart really describes to you the 4 areas, the 4 elements, and where they're addressed and how they should be addressed in applications. And then we also posted this reviewer guidance. This is what reviewers were given to evaluate sex as a biological variable. And it's kind of this flow chart where, you know, it says, does the study involve vertebrate animals or humans? No, then no further consideration. If it's yes, then you go on to the next question. Is the study intended to test for sex differences? If yes, then you want to design, then the next question is design adequately rigorous to test for sex differences. So we thought that it would be very helpful for applicants to really be aware of the guidance that we are providing to reviewers as well when it comes to sex as a biological variable. Okay, and that's it, and I will take questions now. So we do have a mailbox through the disability at nih.gov. We welcome your questions. So welcome your questions now.
Thank you.
Over here.
Our videographer today.
Okay, and now let's see everybody again.
Okay, thank you. Thank you all for sitting through that, and we're very fortunate today to have with us Dr. Stephanie Lindsey, who's going to moderate a discussion, and I know that you will all participate vigorously. I'm just going to tell you a couple of highlights about Dr. Lindsey. Before joining UCSD in 2021, she was a doctoral researcher at Stanford. Prior to that, she earned her PhD from Cornell. Pardon me. Her work lies at the interface of fluid mechanics, numerical analysis, and cardiovascular developmental biology. She seeks to determine causal effect relationships for the creation of cardiac malformations and address important challenges in the clinical treatment of congenital heart defects through a combined computational experimental approach. Would you please join me in welcoming Dr. Stephanie Lindsey?
Hi, so met a couple of you before, and Dr. Jawhead from Nano Engineering, I'm sure how many of you have met her either. So yeah, I guess this is my first time like listening to NIH's spiel on rigor and reproducibility, but kind of also goes to bioethics and how basically the reason that we go into this is to like improve science and to improve healthcare, and that's what should be like motivating you, especially being in like a healthcare at least adjacent or directly in the field. And so a lot of this is to make sure that like what we do actually matters and that other people can reproduce and have access to what we do. So that should be a strong motivator. And some of the things maybe that stood out to me in this video were basically when they were saying that maybe part of it is just really poor training. So I don't know if you guys want to start with just comments on your initial reactions to the video and things that like stood out to you, and if you think that you need better training in certain areas. So for instance, like, you know, and all of the PhD programs, there are like some required classes. And so like, do you think some of the required classes should be giving you like better skills towards rigor and reproducibility? Okay.
I think whenever I have like rigor and reproducibility talks, I always think back to like my statistics training. Because I feel like there hasn't ever really been a formal class. I think you could take a formal class, but it's never been part of my curriculum. So it's all been independent and like what people teach me in the lab or what I've been taught in the lab. And I feel like that's the similar story for a lot of people that are in research.
It is, yeah.
So I don't know. I think there could be something there in terms of, I know statistics, you can literally tell your story, however, as you know, she mentioned, you can hack the data until you get whatever you want to say. So I think if people had a more fundamental understanding of statistics, that could be a good start to understanding rigor and reproducibility.
I think it's an interesting balance, because you want people to have like an adequate background in the math and statistics to be able to apply it to analyzing their data. But then sometimes when you take that step back, people don't always see how it applies to them. So then you also want to have adequate training in the lab, like you have the postdoc or PI or whoever is working with the student. They need to communicate it in a way that the student understands why it's so important. So it's like multifaceted, I guess.
So how many of you have taken a statistics class as a graduate student? And what class are you currently? 219. And it's like a full quarter class,
Well-
not just like a 3 week, like.
It's a full quarter class. I mean, it's interesting, but I think that a lot of the problems actually with the classes that we take, it's kind of like. Most of us had had some sort of statistics class like before, but maybe it wasn't like fully a really rigorous class. But now we're jumping into a rigorous class and, but it's all I mean, like, you want it to be application based, but also I feel like we don't understand the fundamentals sometimes, like.
Yeah, I don't think they call it
Yeah.
a stats class
Yeah,
necessarily.
it's like, but we're using like T statistic and all, I mean, like, they're making us like, they're basically, this class is a data science class, basically. And it's just giving you data and saying, analyze it in all of these different ways, which is in and of itself gonna have statistics. But
But
because
they're not
we aren't-
introducing like the theory behind like what you're using.
Yeah,
so.
it's not. And so, I mean, and most of like, I did a lot of statistics class, but I did mainly probability, like, and less on like actually like dealing with big sets of data. So I thought that it would be more like, let's build it up from the ground up, but it feels more like they're giving us the data and we're using the tools without knowing how the tools are being used or made.
That's what I
And-
got seeing a lot of the graduate classes.
Yeah, and
So
like,
really, the
exactly.
background.
And then one of the things I actually, cause I have a group from my lab is like sitting together and trying to get a better understanding for our work, like what these things really mean. And right now we have this biggest question is like for all these types of things like T statistic and S stat, all that. How do you calculate your degree of freedom? Because it keeps changing. And it's like not very straightforward. And so even if you mean well and you report these values, you may accidentally just do it wrong or not factor in certain things about your, and so I think that's the hardest part. It's like, I know I need to report it, but I have no idea how to calculate that in a meaningful way sometimes. Cause these situations get so complicated. So I think we just need a better stats background.
So I'm like purely computational. A lot of my work is more on the statistical side, or has been, and I know next to nothing about experiments. But besides what the experimentalists tell me, and I think that like having done that kind of work, the perspective on what you need from a stats class is so far from anything I've had. Like if I had only taken the courses and not been doing research in this, I would interpret statistics in a completely different way than I do have like done the research already. An example of that being like with some studies, they're like exploratory data science studies, and other studies, it's like very good scientific design, like they know the questions, the statistical tests will be doing well in advance of getting the data. And with the first type of study where it's more exploratory, I basically only pay attention to like the order of magnitude of your p-value. If you're telling me that your p-value is 0.05, I just don't
Yeah,
care.
but can you always say like, for example, like, I think the fun, like, I can look at a p-value, I can tell you whether or not. For like where I'm working, whether or not it's considered good or bad, but can you always tell how, like, what was your null hypothesis? Like, could you actually describe all that for your situation? I can't always do that. And sometimes they're really complicated, I mean, I think I kind of can, and sometimes I don't even try to, I just look at the p-value and I'm like, oh, that's that. I don't really think about what that meant,
Yeah.
and that I think is not what we should be doing.
Yeah, I agree. I think that there could be a lot more. Even in your basic theory stats courses, there could be a lot more like, how do you actually interpret the statistics in a paper? What's
Yeah.
actually going on there?
Exactly, it would be nice, like, if they, cause I know the importance of if you don't give it an application, then it's really hard to just, cause otherwise you're just gonna be doing like here, get the mean values of, or like get the heights of everybody in like for 10 people, and it's easy to calculate it then. But like, so you need something a little more challenging, but I also think that once we hit challenging, we lose like the actual meaning. Or we just know that that value is good, that value is bad, like sort of deal. which is very subjective on what you're doing, right? So.
How many of you use statistics or like to discuss like with your like PIs about like statistics, like for your sample size numbers, like before you begin experiments or like what you need to acquire?
Yeah, kind of. Or we call it a pilot study. Others.
Interesting, because I teach the undergrad stats course in our department, and we do not have a grad stats course, but I could see as a grad student, when you start doing research and you really have to use this.
I
it could be
agree
very
with that, like,
beneficial.
yeah, and then it's like nice to see it again, like after you know how you're actually gonna be using it, as a grad
But
student.
then the nice thing with teaching undergrads is like, it's the first time they're learning about all this, so I can go to the very basics, talk about, sample size, I don't know, confidence intervals, like where the t-statistic comes from, when do you use it, all these basics, but then for grad, it's just like giving you all these tools to do statistics, right? You have to figure out which tests to do. But here are all the tools to do it.
And also by the time we get there, we've probably forgotten others.
Exactly, that's the main issue, I think, with grad courses is we assume that you have this background and you just took this, undergrad stat course, which is not true, because in undergrad, might have been years away and you probably didn't pay as much attention as you would have if you did it again now. Yeah, so I think it's, at least I'm in the chemical and nanoengineering department, we don't have any kind of stats course for grad, so it would be nice to implement that somehow in some course.
Or maybe like it could be like, we talk about each of like this type of idea, like p-value, t-stat, f-stat, all that stuff. We talk about it like kind of from a basic level, but then you give yourself like a week and homework, it's a little like harder, like you do it with a data set. Or even if it's something like you give us like a paper that we read and we have to interpret what the p-value actually meant. Like not just is it good, but is it, yeah, and I guess I have a question for you. Any like faculty member, do you always know what it means? Like, are you like, very confident in, when you read a paper that you understood what they meant when they reported p-value? You ever find like,
Yeah, it's not always like super.
So, okay, so it's not just me, okay.
Yeah, no, that's you. And that's kind of the problem, right? So like they're saying like, they took all these studies that were like already published and they're like trying to like reproduce them. And that's like, that should be the mark of like doing good science, is that like people can like actually reproduce like what you did because you're like that transparent.
Also, like, do they know what they did?
Like,
Because a lot of
yeah.
this,
In your own lab, like, that's the question, it's like, are you producing?
we're
this
doing
at
that,
least?
we're
Yeah,
attempting to.
exactly, so I mean, like, maybe some of these, can't even reproduce it in.
Yeah,
their
you're like
labs.
maybe like can't even reproduce in there.
And some of it comes from, like the student's gonna graduate, the grant is gonna run out, so we've done, 20 experiments, n equals to 30 for each. We've done that and it was reproducible, but we didn't try beyond that, we got our data and we moved on because the student graduated, so there's some, like, things that we can't change about science, unfortunately, there's limited resources, but.
But you report it though.
But you report it,
Yeah, exactly. You report it and you just like share it like all
That's true,
your.
but all these arbitrary, like n equals to 30 or like p is less than 0.05, these are just, arbitrary, really, if you
Yeah.
think about it. Like if you have 30 cells versus 150 cells, of course, 150 is better. So do 150 if you can, but you do the bare minimum just because that's your limited resources. But yeah, it all depends. Statistics depends on what you're studying. You can study 3 mice, but if you're studying cells, you can count thousands of them.
It's like
just
also
about
really
resources.
surprised that they're like, people's cell lines, but I think like 30% of like cell lines are like not what people think they're using.
Yeah.
What?
We had several papers come out. We were buying cells from a company and then the company came out and said it's not the type of cell that we thought. So those papers are still out there and we're not gonna go retract them.
No.
We were doing tool development, so it didn't impact our studies too much, but this happens.
Yeah,
in
so that's the
science.
problem. Yeah, exactly. It's like people put bad data out there and then like if you're trying to like confirm you have the actual right thing, you could be comparing against all the bad data.
That's something else I
Actually.
wanted to was, they asked to validate your key biological resources that you're using, right? But the amount of energy and effort
Exactly,
it would
right?
take to
Yeah.
actually validate every single antibody, every single cell.
Yeah,
every single
exactly.
cell.
You're like, you have to trust these like repositories that you're like buying from.
Yeah.
This
Yeah.
is where I bought it
We
from.
weren't testing.
And then you're like, okay, according to the literature, it should have these markers. We see these markers. If they're wrong in literature, I don't know what to tell you.
Really good at telling us what to do to change our way, but then they could change their ways by, first of all, giving them enough money to do all the things that they're asking for. The money that, like just authenticating the key biological, it's that costs the money that they give you as a whole grant. So they should change their ways to some extent too. But I mean, we can change our ways a lot. But it's true that like science has limited resources, and unfortunately that causes bad science in some ways.
Yeah.
So some of it is just, you can't avoid it, but then there's a lot of things that we can do. For example, actually, this was in my lab meeting just a few days ago. One of the students was showing their results, and then the other student was like, change your standard deviation to standard error so the errors look smaller. And then this conversation started about like, what does standard error mean? What does standard deviation mean? And when can you, or can you ever use standard error in the kind of research that we do? And, you know, not everyone in the group knew about this. And so we're finally reading papers just explaining like standard error is never acceptable for our work. It's just calculate confidence intervals. You always use standard deviation. You can't just change your statistic to like reduce your error bars. So like these are
But
things
if
that,
they're reporting that you're using standard error.
it
like,
depends
then
on what
people
you're saying.
know that you're.
yeah, but you're not, but there's some, you can report it, but then later people will see it's just inaccurate to use it. Cause standard error depends on what there's some.
It's like standard deviation divided by the root of your like
Yes,
population,
which is
right?
used to calculate confidence intervals, but not to show the distribution of your data. This is like, there's a few papers on this. I know it's not very straightforward. I encountered it once, but you're not supposed to use standard error to just reduce your error bars. You can't divide it by the square root of your n. Especially when your n is small. It's like you have 3 samples and you average them. And then imagine your standard deviation will look half the size. I can send a few papers on this if anyone wants to read about it, but yeah, because most of the time you cannot use standard errors. Standard errors is only to find your confidence intervals. Because then you multiply it again by your, so if you can search this if you want to read about it, when it's appropriate to use standard error, almost never.
I haven't been, but that's interesting now.
I know, 'cause it's like, if they say it's standard like error, then you like know what it is. I mean, I don't know, like.
Sure, yeah,
like-
you can say it's standard error, but it's used, you can't use it for showing like the distribution of your data. You have to use standard deviation,
Also, one thing I'm
and so many papers do it, so it's a common, very common.
Yeah, and like, I thought, well, like read the like figure legend to know like which one they're showing, and then you know like how to take
Sure,
it into
and
account, so like then
some
like.
type
why
of
should
studies you
it?
can use standard error, yeah.
Yeah.
One thing that I'm also starting to notice is that, so a lot of the tools I think people are using, whether that be like for imaging, like some sort of like statistical analysis or analysis of what you're looking at. A lot of times they pop out these values like p-values and f-stats and t-tests for you. I don't actually think the people who are reporting it in paper knows it is. They're just saying, oh, yep, that's low. And they're putting it everywhere. And I think that is, you know, why it's so, why they don't specifically write what, you know, like, they're not more specific about what they did and like what they're measuring. And they just put the p-value at the top of the plot and they're just like.
And they just don't know what it is.
They have no idea what it is. I'm like, especially, I see it a lot with, cause I work a lot with brain data and a lot of people who are using our scanners are usually like psychology department area and stuff like that. And I mean, I get it. These algorithms are really complicated and crazy. And you just want to have a nice little report at the end. And so it does, it pops out a report. And people, that's what they report, you know, in their papers, but that doesn't mean they do what they're doing. And so the question is how much, I mean, I don't mean it in a bad way, how much is it okay for you not to understand the tools you're using? Is it, I mean, you have to have some sort of abstraction, because you can't know everything and reinvent the wheel. But when is it like you're turning a blind eye to something that's really important? Is a hard question.
So I teach like numerical like methods classes, and like this is, I mean, and a lot of times like students are like, why do we have to learn this? There's a MATLAB tool that will just do it. And you're like, because whatever tool you're doing is making like all of these like assumptions. And like you have to know like how they're calculating it to know like how much you want to rely on like what they're doing. And so like if you're dealing with like these huge so like huge matrices, like really big problems that you're like modeling, then like their small, like whatever they did and like their like nice little tool like propagates to like these really big like errors, and it might not be what you actually want to do. So yeah, so, and it's also a reason why like, so. A lot of biologists like want to become like more quantitative, and I think it's kind of a responsibility of like engineers to like know the math and know what you're using, and like, and so like any quantitative thing you should know about. And so for instance, like we use ultrasound a lot to evaluate like the cardiac assessment of like how our embryos are like doing or how our animal models are doing. And like in ultrasound, you can now like calculate, like they have like these different modules, and like, oh, we're calculating strain, and like we're calculating all of these things. And I'm like, and the software is proprietary, right? And so like strain is not like something that you report in like a percentage. And that's what this like, you know, that's what the machine like spits out is like strain. It's like a percentage. And you're like, you don't know what you're talking about. But then that starts dominating the literature, right? Because it's like so anyway, so we like, that's one of the reasons why if it's proprietary software and I don't know like how they're calculating it, I want to use it because I want to know exactly like what's being done if I'm gonna like report or rely on this value. And I think like
For everything, like there's never a time where, cause I'm like, I get it for like things that are easy, a little bit easier, like statistic, like kind of like. Basically to measure how the quality of your data and stuff like that. I get those, but especially with some of these pipelines where they're doing a lot of. Like I use a pipeline that denoises images, basically removes signals we don't want and keeps the ones we do for like fMRI type stuff.
yeah.
But it's making some pretty big assumptions when it does this, and we're spending a lot of time, I think, like actually validating what we're getting, and because we're working with some new data that it's never like, seen before, and it's not doing so well. But so that's good. But I know a lot of people that just take this like they just this is like standardized. They just like, yep, we ran it through this pipeline. Here's what we got. See, it works. And no one is doing exactly what we're doing, but the question is like, is it necessary for every single?
person to validate it.
Yeah, because it will take forever, I mean.
Yeah.
And I see why it's necessary for me, because I'm using a new type of data that's never been put through this before. So we have to actually see if some of the assumptions are making true for this data too, and that's where we're starting to see it fail. But for data that's more standardized, maybe it's
Yeah.
okay to make the assumptions.
Exactly, so for data that is more standardized, it is okay because it's already been like validated.
Mhm.
Like, I mean, so for instance, like I do like computational fluid dynamics, and like everyone like has their like own in-house solver because they're always coming up with like new like applications that like it's easier just like annotate your own code and like integrate into it. And so like the first thing that you do when you like write your own solver is you run all the classical fluid mechanics, like flow past a rotating cylinder, like all the classical cases, and show that you can reproduce like all these like literature of like you do out the mathematical problem, you do the experiment, and like we're replicating that. Then I'm like, okay, any fluid problem that I'm doing, I'm not gonna like, I trust like what is in there, right?
Yeah.
So it's like, how is this, like, you don't necessarily have to be the person who's validating it, but like you see like that it was properly cited and validated, and you like, so knowing that you can trust the foundation it was built on. And then like, if you're testing like the limits of it, like you're applying it to something that no one's tested, then I think it's like, that's why you would need to validate.
I think it's interesting also in the interdisciplinary science area. Cause it's not just like people with more of a biology background coming into more of the mathy stuff, like how they understand how the statistical tests work, how whatever computational tools they're using work. But also like people with more computational backgrounds going into the biology and making sure that they're checking for all of these like genes that a biologist would know to check for, that a physicist might not know to check for. So it's on both sides too. So it's. The interdisciplinary area is interesting.
It's true. I know there's another resource problem, but I know some labs have statisticians that are consultants to their lab.
Or departments,
Yeah.
just like have like a statistician that like, I mean, I did my PhD at Cornell, and it was like all like, you know, like you have an office where you can go and like consult people on like statistics for like coming up with your experiments, for verifying it while you're writing your papers and like all this stuff. And like all these departments like paid into it, and like you could just go to the office and make sure that you're confident and like and then what you're doing. So like,
Research, like we have people who don't really wanna do the math, it's fine, like it's gonna take forever for them to have to do all of that.
yeah,
And
and
if you
like,
have some center.
and maybe
or
it's
just one or two
unaccessible to you,
people-
you know, like maybe mine doesn't work that way, so like.
We
Doesn't
still
mean you
wanna
can't
do
do
good
work.
science, exactly.
Like, you just need to
We
work.
wanna be doing rigorous,
But also the question is how, I can't imagine that. I, maybe that they're just trained in a specific way, but how do they like apply it to every, like, you come in with a brand new problem they've never seen before? and
They can, it's just, I mean,
I mean, I just think
explain
it's
the
like people who
data.
got PhDs in statistics and that's what they
Yeah.
want. It's like
Types of
applying
data.
it.
No,
to
but
different
I guess
things.
the purpose is for, so for the project in the program I'm working on, most people have tried it with three types of images put in through this thing. Mine is 122, which is very different. But most people wouldn't think it like, you know, because they've tried it with a couple of numbers, it's just we're all under 10. Just based off the data and how it was acquired, but because we're working with a scanner that they don't know. And it's a completely different acquisition, but we got the same images out. It would be a completely different test and it can get really mess with the numbers that they're getting. So I don't think someone who necessarily would know to think about that. If it's to them, it's just a scaling up in a number, not anything else. So how would they know that would cause a problem, especially if you tested a little bunch of small numbers and it all worked? You know, you went from 1 to 10 and everything worked fine. But you go to 122, I wouldn't think it would stop working, but the inherent physics of the problem.
Yeah, I think consultants in general are not like expert in your area, but they can.
And that's why you go,
Give
you
you-
talk to them,
exactly,
you're
and they
talking
give you
about all these
ideas about-
limitations and like,
But that
they
would
ask all
mean-
these questions.
That would mean
so.
you'd have to have some knowledge, right? Like that, like you couldn't come,
Statistics,
yeah,
but
but, no, I mean like, so it couldn't just be, you would have to still be able to ask the right questions.
sure, exactly, yeah.
Which
You
is
have
still-
that specific.
So you still have to know a little bit, or for them to actually be able to help you correctly.
Yeah, or you have to explain, they're like, oh, well, that's not possible for me to do it this way for these reasons. Like, so they'll suggest like one way and they're like, oh, I already know, like, this is not possible, and here are the reasons, and then they can like work with that and share.
And that's
with
what
them.
they're working with.
Yeah, exactly, so it's like a back and forth, and doesn't even have to be just like one meeting, and you're like, I tried this, and like, this is why it can't work, but anyway, we don't have. any-
Nice. That's what we want is-
I was meeting at 2, so I have to run.
Thank you so much for coming.
We should get that. I'm pretty sure I'm pretty sure I'm the stats consultant, I'm just not very good.
There's a center on campus.
Oh, really?
It's called BERD, BERD, Biostatistics, Epidemiology and Research and Design. So like you can go in with your animal model and they'll be like, yeah, that's legit, or no, like you need to do something else, like,
Cool.
Yeah, so maybe sometimes it's just like knowing like what you can like access. I don't know, sometimes I like see there's so many centers and stuff like at UCSD. You contact them and they like don't exist anymore, or it's just like one person's lab that they like called like a whole thing and that person's like, I want sabbatical, but I don't. But check out.
Interesting.
Yeah. Any non-statistics comments like what you brought about like, yeah, regarding reproducibility?
They did mention like negative results of being able to publish and get promotions and stuff for publishing negative results, which seems like it would really, really help with this problem. But I don't know any like initiatives that MIH is taking to actually do that.
Yeah, I don't
Yeah,
think you're gonna get
yeah.
like grant
Yeah.
money for that. I mean, so basically like in research, your currency is publications to show that like you can be like productive. And there are journals that will like accept like publications, like even some of the PLOS journals will like accept like publications like that you should like, I mean, basically negative results that will help people like not go down a certain path. And so then like when you are doing your NIH grant, you're like, we're proposing this new way because we know this way doesn't work, and you cite your publication. So it still can help you like towards that. I mean, yeah, but it's like you do have to like get it published somehow first. For it to like count as more. I mean, so for instance, like, I know both in like nano engineering and mechanical engineering for our promotion files, they literally count the number of publications that you have and look at like what journal it's in. They're like, how good is this journal for like their particular field? Which, I mean, it's not a very like, I mean, it's not a very thorough or holistic way of evaluating your science, like what you're doing, but it's just like, it's the game that like, I mean, and basically the culture that's like been created around like publication. So, but one of those papers could be negative results. You just have to like have given it to the right journal.
Right, yeah.
Yeah, what journal is that?
No, but seriously, not nature. Not science, it's not self. But seriously, like, for instance, like class computational biology, like, I mean, that's a journal that I would publish in, and they accept like basically negative results. So it's just framing it in the right way that like people can take away something from like what you did. So it's not like, so it's like, it's like, I have no results to show, like, no, you're not publishing that. But I did all this work, and like, this is what I expected to happen, and this is like what happened, and like people will still accept that. Like,
Also, I mean, I would feel like they would want a decent reason why, like at least, or some testing to actually prove why that happened, and that's not easy. Like that's like another couple of years of research on top of something that, you know, you're almost done, finished, you just realize you got like something good result.
I mean, maybe like depends, like maybe they want like mechanisms, like depending on like the type of journal, but you know, there are like, for instance, there are, I mean, there are journals where you can like basically like just publish like all of your histology, like and stuff like that. I mean, I
don't think that works for MRI.
but I mean, you can like publish all your images.
Just here go.
And be like, so yeah, I mean. There are a ton of journals, but you do want it to be, so part of the way that you can like disseminate it as well is like in your research talks that you like give. And so then like people are like drawn to them, like what you're saying, and then they're more likely to like cite it, even if you published it in like a, you know, a journal that people don't normally look at. And then they're like, oh, that helps our case with this, and that helps explain something that we were seeing, and then they start citing like your work as like evidence.
But like, if you submitted a grant to the NIH and aim one was, hey, this entire grant proposal relies on a previous study, aim one is just gonna be checking that previous study. Like, it's hard to imagine that would be accepted. But that seems like helpful work for someone to do.
I think it's what you'd have to do, but
You
it's not
have
what
to
you're
find-
saying is
Yeah.
one.
Yeah, exactly. But you have to find like, I mean, yeah, so like, say like you didn't work at mechanisms yourself, but there's like, you have a bunch of like hypotheses, because that's what they want. It's just like a bunch of hypotheses with evidence that supports it, which we can find for basically anything. So it's like, so you're like, this didn't work, I'm citing my study, and like, I have all these ideas that I didn't explore about like why it didn't work, and here's all this evidence that supports my idea. Like that can be like. Okay, I think so, we're at 2. So we can wrap up if anyone wants to say any last thoughts. I mean, I think everyone's motivated, well.